Hi folks, this video talks about addition of water to alkenes through either acid-catalyzed hydration or oxymercuration-demercuration reactions. Hydration of an alkene refers to the addition of water across the alkene pi bond. This water will be added in the form of an H and an OH group. This reaction will occur in the presence of an acid catalyst. The reagents for acid-catalyzed hydration of alkenes can be written in a few different ways. One way is writing H2SO4, sulfuric acid, as well as water. A second way of writing the reagents is to just write H3O+. Or a third method is to write H+, a proton source, as well as water. The hydration of alkenes is regioselective. Notice that in each of the reactions, I added the hydrogen to the less substituted carbon, and the OH group to the more substituted carbon. We would call this a Markovnikov addition, because the OH group has been added to the more substituted carbon. And when I discuss the mechanism on the next page, you'll see that this product forms selectively because it came from the most stable carbocation intermediate. The reason the reagents written all three ways are equivalent is because when you dissolve a strong acid, written as either H2SO4 or just H+, and you dissolve that in water, it immediately turns into H3O+, known as hydronium. So here's an acid-base reaction where sulfuric acid is acting as the acid and water is acting as the base. Looking at the pKa for sulfuric acid compared to that of the conjugate acid, H3O+, H3O+ is a significantly weaker acid, and the equilibrium would heavily favor the product side. So even if you started out with sulfuric acid and water, immediately you would form H3O+. And so we're always going to draw our acid catalyst as H3O+. I'll show you the hydration mechanism for this particular example. I'm starting out with a tri-substituted alkene. One carbon is less substituted, and this is the one that has the hydrogen added to it in the products. And the more substituted carbon of the alkene gets the OH group in the products. This carbon that forms the new bond to the alcohol group is chiral in the products, and you'll form two different products here that are stereoisomers of each other. I'll show you why this arises in the mechanism below. The mechanism begins with a proton transfer. The alkene will act as the base, and H3O+ will serve as the acid. I'd have two curved arrows from the base to a hydrogen, break the OH bond, and bring those electrons to oxygen. I need to consider which hydrogen of the alkene to add the proton to. If I add it to the left carbon of the alkene, the following carbocation would form. Or if I added the hydrogen to the right carbon of the alkene, a different CH bond would form, and a different carbocation would form here as well. To decide which of these carbocations would form, I need to look at their substitution. One carbocation is tertiary, and the other one is secondary. When I draw the mechanism to form the major products, I should only draw the tertiary carbocation intermediate here. Always assume that you'll form the more stable carbocation. So I should actually ignore the secondary carbocation, and I will only focus on the tertiary carbocation, which is more stable, for the remainder of the mechanism. In the reaction mixture, I have a tertiary carbocation, which is a strong electrophile. And assume that if you have H3O+, you have water around as well. Water can serve as a nucleophile, whereas H3O+, the oxygen already has a positive charge, so it is not nucleophilic. It would take a lone pair from water and bring it to the carbocation. This step forms a new carbon-oxygen bond, and the oxygen has 3 bonds and is now cationic. Notice that with the oxygen added to it, the carbon that was formerly the carbocation is now chiral. Because the carbocation intermediate was planar and sp2 hybridized, you can consider water as the nucleophile adding from either above or below. If water adds from below, the stereoisomer with a carbon O- would be formed, or if water added from above, the stereoisomer with a carbon-oxygen wedge would form. Notice that these are looking similar to the products as I drew them up above, but they still need to lose a proton to make the oxygen neutral. To get to a neutral alcohol product, I can bring in water, which can serve as a base. Assume that since water is your solvent, you have plenty of it around. I'll use a lone pair of a water molecule to serve as the base to deprotonate the cationic oxygen. The proton transfer that I've shown would get me to my product where I have the neutral alcohol where the OH group is a dash. Then I could imagine a proton transfer using water as a base to deprotonate my wedge OH cation. This proton transfer would get me to my neutral alcohol product where the OH group is a wedge. This final proton transfer, where water is acting as the base, is going to form H3O+. H3O+ is actually a catalyst for the addition of the H and OH groups across the alkene. And recall that catalysts are supposed to accelerate a reaction but not be consumed. Therefore, it makes sense that we're remaking an equivalent of H3O+ at the end of our mechanism, so it could go on to catalyze another one of these reactions. There's an interesting trend that's observed in the alkene substitution effect for acid-catalyzed hydrations. Let's consider the following 3 reactions. In one case, I'm starting out with an unsubstituted alkene. In another case, I'm starting out with a monosubstituted alkene. And in a third case, I'm starting out with a disubstituted alkene. In the second 2 cases, I've shown the Markovnikov addition product, where I've added hydrogen to the less substituted carbon and OH to the more substituted carbon of the alkene. Interestingly, these reactions have wildly different reaction rates. Having a single methyl group on the alkene makes this acid-catalyzed hydration reaction 10 million times faster. If you add a second methyl group to the alkene, the rate compared to the unsubstituted alkene is that it proceeds 1 trillion times faster. To see why this is the case, let's consider the carbocation intermediates that are formed in these 3 reactions. In the first case, a primary carbocation is formed. In the second reaction, a secondary carbocation is formed. And in the third example, a tertiary carbocation intermediate would be formed. What these reaction rates show us is that the more stable the carbocation intermediate is, the faster this acid-catalyzed hydration reaction will occur. Similar to hydrohalogenation, where we saw that the addition or elimination reactions could be favored under different conditions, it's also possible to have addition of water or elimination of water. the outcome of whether the alkene starting material or the alcohol product will be favored depends on the concentration of water used. The reaction of taking an alkene and adding water to it to form an alcohol product is known as hydration. And the process of starting out with an alcohol and making an alkene and water from it is known as dehydration instead. The reaction conditions to use to favor the formation of the alcohol product is to use dilute sulfuric acid in water. Instead, if you want to favor the dehydration reaction to form an alkene and water, you would use concentrated sulfuric acid instead. We can explain which side of the equilibrium is favored by considering Le Chatelier's principle, where we're looking at the concentration of water. Think about the dilute sulfuric acid conditions as being conditions where you have a lot of water around. As you make the concentration of water starting material high, by Le Chatelier's principle, you push your reaction to favor the product side more. If instead there is not very much water around, as is the case when concentrated sulfuric acid is used, the reaction will proceed backwards to make more water. So I want you to remember that if you treat an alkene with water under dilute sulfuric acid conditions, you will favor the formation of the alcohol product. If instead you treat an alcohol with concentrated sulfuric acid, you'll favor the formation of an alkene, and water will be formed as a byproduct. Because a carbocation forms in the acid-catalyzed hydration mechanism, carbocation rearrangements are possible. Let's consider an example of starting out with an isopropyl substituted alkene and treating it with H3O+. These are acid-catalyzed hydration conditions. The expected products of Markovnikov addition of water are that you would add hydrogen to the less substituted carbon and OH to the more substituted carbon of the alkene. In this case, the carbon that gets the OH group in the product is a chiral center, so we need to draw both stereoisomers of product. One where we added the OH group as a wedge, and one where we added it as a dash. It turns out that these are minor products for this hydration reaction. The major product is where the OH group has added to a different carbon that was not originally a part of the alkene. This corresponds to the central carbon of the isopropyl group in the starting material, and the fact that the OH group added to it in the product suggests that a carbocation rearrangement must have occurred. The first step of the mechanism is a proton transfer. I'll use the pi bond as a base to deprotonate H3O+, the strongest acid that I have available in solution. This proton transfer adds the hydrogen to the less substituted carbon of the alkene, and the carbocation forms at this secondary position, the more substituted carbon that was formerly a part of the alkene. A rearrangement reaction can occur to convert this secondary carbocation into a tertiary carbocation. To do this, I'm going to show a hydride shift. After the hydride shift, the carbon that was formerly the carbocation has a new hydrogen and is now neutral, and the carbon that lost the hydride has become the carbocation. In this case, it is a more stable tertiary carbocation compared to the previous secondary one. The carbocation is an electrophile, and there is water solvent around that can behave as a nucleophile. The nucleophilic attack takes a lone pair from oxygen to form a new bond to the carbocation. The next intermediate features a new carbon-oxygen bond, and the oxygen still has 2 hydrogens attached, and it is cationic. To get to a neutral alcohol product, where here I'm trying to get to the major product specifically, I need to do a proton transfer. I need to bring in a base, and the best base that I have available between H3O+ and water is water itself. This proton transfer generates the neutral alcohol product. A set of reactions, known as Oxymercuration-Demercuration, is useful if you want to add water across an alkene and if you want to prevent carbocation rearrangement from happening. The reagent for oxymercuration is known as mercuric acetate. This involves a mercury attached to 2 acetate groups. The acetate group could be drawn out like this, attached to mercury, or it's often abbreviated as OAC. It's possible to have a loss of one of these acetate leaving groups from mercury. This forms a mercury with 1 acetate group remaining. The mercury is cationic, and it forms an acetate anion as well. This cationic mercury with 1 acetate attached is a very strong electrophile, and we're going to use it as an electrophile in the mechanism. The first stage of the mechanism is called oxymercuration. This begins with a nucleophilic attack, where the alkene pi bond acts as the nucleophile and the mercury cation acts as the electrophile. I would draw this as a curved arrow from the middle of the pi bond to mercury. I would show a new carbon-mercury bond to the less substituted carbon that was formerly the alkene. And the more substituted carbon has lost its 4th bond and is now cationic. The difference between the groups we've added so far to alkenes and mercury is that mercury has lone pairs. Using this mercury lone pair, there's a second resonance form for this intermediate that can be drawn. I'll get to this other resonance contributor by taking the mercury lone pair and bringing it down to the carbocation. In the other resonance contributor, mercury still has its bond to the less substituted carbon, but it now has a bond to the other carbon that was formerly a part of the alkene as well. There's a 3-membered ring with 2 carbons and the mercury, and the mercury now has a positive charge. In the resonance hybrid for this intermediate, the carbon-mercury bond for the more substituted carbon of the alkene would be a dotted line, and both mercury and this more substituted carbon of the 3-membered ring would have partial positive charges. This is where, in my resonance contributors, I have full positive charges. In the next step of the mechanism, I'm going to bring in a nucleophile. This nucleophile will have a bond to a hydrogen that can be lost in the next step of the mechanism. And it is this carbon of the 3-membered ring with the partial positive charge on it that's going to serve as the electrophile. I'll bring in this nucleophile to that electrophilic carbon, and I will break that carbon-mercury bond. You can think about this as both a nucleophilic attack and a loss of leaving group from that more substituted carbon in a single step. After this nucleophilic attack, there would be a new carbon nucleophile bond at the more substituted carbon, and the less substituted carbon retains its bond to mercury. The more substituted carbon is now a chiral center, and so I need to draw my new bond to the nucleophile as either a wedge or a dash. If the nucleophile was neutral starting out, it is now cationic in this intermediate. To get to a neutral intermediate, I need to deprotonate the nucleophile that's cationic in my intermediate. Imagine that you have plenty more of your nucleophile around, imagine it's your solvent, and that it can act as a base in a proton transfer step. To either of my stereoisomers, I can bring in this nucleophile as a base to deprotonate my intermediate. I've gotten to 2 neutral stereoisomers of product. Looking back at my original alkene, I've added a new nucleophile to the more substituted carbon, and I've added a mercury to the less substituted carbon. This whole part is known as the oxymercuration part of the mechanism. The first intermediate that we formed is different from what we've seen before because it's not a true carbocation. There's some special resonance involving mercury and its lone pairs. And it is this mercury and resonance that prevents carbocation rearrangement. The second part of the mechanism is known as demercuration. You don't need to know the mechanism for this step, but I want you to know that the reagent is NaBH4, and it has the effect of removing the mercury in the acetate and replacing it with a hydrogen. Here are what my 2 stereoisomers of product would look like. Looking again at my original alkene, the net effect after this demercuration step is that a nucleophile minus its hydrogen has been added to the more substituted carbon of the alkene, and a hydrogen has been added to the less substituted carbon of the alkene. So, ultimately, the reason to use oxymercuration-demercuration is that it avoids carbocation formation. So if you don't want carbocation rearrangement to occur, this is a safer bet than H3O+. Recall that for that isopropyl substituted alkene, treatment with H3O+ gave a mixture of products. The major product was the result of a carbocation rearrangement. Let's consider that instead you wanted the other product, the minor product, where a carbocation rearrangement had not occurred. A way to get this product instead is to treat that alkene with the oxymercuration-demercuration reagents. The first step will involve treatment with mercury acetate and water, and the second step is treatment with NaBH4. These 2 steps would give you the product where you add hydrogen to the less substituted carbon of the alkene and OH to the more substituted carbon of the alkene. If you generate a new chiral center, both stereoisomers of product will be formed, but no rearrangement will occur. This OH group in the product came from the water in the first step, and it will always be the case that whatever nucleophilic solvent you use in the first step appears in your product at the more substituted carbon of the alkene with a hydrogen removed from it. So let's consider you started with the same alkene, and you had the same reagents for oxymercuration-demercuration, except that you substituted in a methanol solvent for water. Your reaction would add hydrogen to the less substituted carbon of the alkene, and then you would add your nucleophile minus its hydrogen to the more substituted carbon of the alkene. In this case, it would appear as an OCH3 group in the product. Here as well, use of the oxymercuration-demercuration conditions avoids carbocation rearrangement. This choice of the nucleophilic solvent is very flexible. So imagine yet again the same alkene and the 2-step mercury acetate and NaBH4 reagents, but here instead of water or an alcohol, I have an amine. In this reaction, I will add a hydrogen to the less substituted carbon of the alkene. I will add this nucleophile to the more substituted carbon of the alkene, and this nucleophile will lose a hydrogen to form a neutral final product. So my amine started out with a methyl group and 2 hydrogens, and in the neutral product, after the amine has lost a hydrogen, it will be a neutral nitrogen with 1 hydrogen and 1 methyl group. Here as well, I generated a new chiral center, so I have both the wedge nitrogen and dash nitrogen stereoisomers, and no carbocation rearrangement occurred. Alright, so in summary, today's video introduced the addition of H and OH groups to an alkene. This can be done using acid-catalyzed hydration. One shortcoming of acid-catalyzed hydration is that it involves a carbocation intermediate, so carbocation rearrangements are possible. If you don't want a carbocation rearrangement to occur, you can instead use Oxymercuration-Demercuration, which goes by an unusual mechanism, but it avoids the formation of a carbocation, so you don't get carbocation rearrangement under these conditions. That's it for this video. I will see you in class.